Hi, I'm Sarah Krisch.
And I'm McGullam. This is Group 22 in our glider project report.
So for this project, the goal was to make a small glider out of balsa wood that could fly for as long as possible in a straight path. And in order to do this, we would have to do research and follow the design process with iterations. The name of our glider was Big Red, inspired by the plane in the Peanuts comics. The requirements for this glider were first size dimensions, meaning it had to be less than 16 by 16 inches, a successful test flight. So the minimum it would go, the goal was 20 feet or to be more than 20 feet. And the third requirement was it had to be a glider. So it had to include wings and it couldn't have any sort of engine outside of the hand we used for propulsion. During design, we considered a lot of alternatives. First was wing shape, considering elliptical wings versus tapered wings. Pros for the elliptical wing was lift and even lift across the whole wing, so the lowest theoretical drag. But the con was it doesn't stall well or react to wind well, so you can lose control easily. For the tapered wing, pros were allowing for faster speed of the glider and wind speed, and the con is that it does have more weight and more drag than an elliptical wing. Wing placement, wings closer to the front or the back. If it's closer to the front, there would be necessary weight in the front and reduced pitch. But if they're too close to the front, we would have to correct the center of gravity in some way, which would decrease lift, and then the wing and tail configuration would be really far from one another. Whereas if the wing is close to the back, it does not have many pros, but the cons is that there's not enough weight in the front, and then the glider would lean back and not fly well because the forces are unbalanced. So overall, for a successful glider, balance between these needs to be reached, but wing placement should be closer to the center and the front to account for both pros and cons. For wing placement, we also considered angled versus flat wings. For angled wings, pros reduce drag and reacts well to stalling, whereas the cons are less stability at lower speeds and it's more complex to build. And for flat wings, although it's easier to build and stable at lower speeds, it results in higher drag and less ability to react to stalling and wind. Finally, for the tail configuration, first would be conventional, which reduces drag and is easy to balance and make symmetrically, but the cons is that it could be damaged easily. The T-shape configuration, pros would that it would provide more stability, reduce drag, but cons are at higher chance of stalling from high angles of attack, and it's more difficult to construct. And then the V-shape is there's less weight, which has a lower center of gravity and less likely to be damaged, but the cons are that it again is difficult to construct. So when evaluating all of these different alternatives, we decided to do the wing shape as elliptical because they produce the greatest lift and low drag, and we would be flying at low speeds. For our wing placement, we decided to go towards the front and center and make them angled so that it would be closer to the nose to have enough weight in the front, reducing pitch, and our angle of attack was 0, so we made the tips of the wings higher than the roots to reduce drag. And then for the tail configuration, we went with conventional just because it would be easier to construct, reduce drag, and maximize our structural integrity.
We decided that the ratio of wingspan length to fuselage length should be 6:1 or 4:1, and that the ratio of wing area to horizontal stabilizer area should be about 4:1. And we based the size of the vertical stabilizer on the size of the horizontal stabilizer, so the bases would line up evenly. And then we adjusted all the values after testing the glider, increasing the wing area, decreasing the size of the horizontal stabilizer, and increasing the size of the vertical stabilizer and fuselage length. Because we had elliptical wings, the chord length was equal to the root chord length, and the tip was just 0. The root chord length was 2.39 inches, the wingspan was 14 inches, horizontal chord length was 1.58 inches, and the horizontal tailspan was 6.7 inches. The wing location was 2.58 inches from the front. The fuselage length was 10.61 inches from the front. This is our first design and test. We determined that the center of mass was right behind the wing, so we wanted to add weight to the front. The first flight was included too much pitch, so we added Play-Doh to the front, again, adding weight. The second flight went straight for longer, but still stalled back and lost control. There was no problem with stalling after the third flight because we added enough Play-Doh, but we added a little bit more to the left wing because it started to curve to the right. The fourth flight, it went straight up and then downward and seemed to experience drag. So we added more weight to the front, and the fifth flight, it spun out to the right. Wing and vertical stabilizer broke off, and we did not have a straight path. We decided to increase the size of the wings to increase weight towards the front and increase the lift. We moved wings forward more to distribute weight towards the front and stabilize pitch, and making horizontal stabilizer smaller and vertical stabilizer larger, keeping the shape of these components to decrease the weight in the back. Our final design had a fuselage length of 11.25 inches, the chord length was 2.25 inches, the vertical stabilizer was 2.44 inches tall, and the horizontal stabilizer was 5.31 inches wide. The wings were of elliptical shape and were slightly angled up. For flight day, Play-Doh was added to the front to add weight to the front of the glider, so it would fly straight and to the right wing, because we noticed it was going to the right also. We estimated the center of gravity by balancing the glider on one finger, and we decided that it was 4.5 inches from the nose of the glider, which was about 0.8 inches from the quarter chord location. We estimated the coefficient of lift using the equation coefficient of lift equals 2 times weight over sea level air density times velocity squared times the area of one wing, and that we found to be 0.2096. We estimated the coefficient of drag by first finding the induced drag, and then because the induced drag was equal to the zero drag, we found that the coefficient of drag was 0.0017. Increasing the size of the wings allowed for more lift of the aircraft. One of the biggest issues we were having was the pitch, so we added more weight to the front, and this fixed that problem. And we did that using Play-Doh. And we increased the size of the vertical stabilizer to decrease the chance of yaw in the glider. There was more stability because of this, and we maximized the distance the glider would travel without turning.
This is the video of our best test flight, which goes 35 feet.
Our Big Red glider did meet the requirements. At competition, it consistently flew over 20 feet at 22 feet, and its maximum flight was 35 feet. The size requirements were met, and the wingspan was 15.375 inches, which is into the 6 by 6 inch range, and the fuselage length was 11.25 inches. It flew straight from our throws and was overall symmetrical and well built. This was a very educational project. We used a design and iteration process, and we learned to use pros and cons of alternative designs to put our knowledge of components of a plane to use. Further improvements to consider in the future would be having more iteration in design. We only got to observe making changes to wing size and placement, but in the future it would be ideal to determine the best adjustments for all aspects of the plane. This includes trying different angles for the wings and different wing shapes.
And this is our list of references. Thanks for watching.